Hi, I'm Sala, and in this video we are going to discuss a model-based approach to control of total flow and the concentration, the degree of dilution of a given reagent in a static mixing process. The motivation is somehow a plant like this, in which a reagent is diluted in water and heated to a given temperature, and we need to control concentrations, levels, flows, whatever. There are other videos in this collection that discuss a common sense approach on how to control this. In this case, we will concentrate on the mixing part, we'll forget about temperature, and also we'll consider only the master control that will send set points to these slave flow control loops. The dynamics of the mixing in tank 1 and 2, heating and level, will not be considered for simplicity and brevity. In this first video, we will only discuss the modeling of the static mixing sub-process, its linearizations, and the multiloop pairing that the relative gain array procedure recommends. In forthcoming video, we will consider more advanced options such as ratio control and decoupling. So let us consider the modeling part. We realize that the above tank system can indeed be considered as this overall thing. First, level will depend on total flow, not on the concentration. Of course, there will be disturbances, whatever, that we would need to handle in level control, but we are not going to consider it. And on the other hand, this lower part of the picture depicts the fact that concentration after the mixing of the two inflows will propagate through some dynamics, washing out the tanks or whatever, depending on the steering in tanks or things like that. And at the end, we'll have some outlet concentration that, of course, if this reagent fraction is kept constant, then it will end up being equal to the inlet concentration. But that G1 and G2, this level and tank concentration dynamics, will not be considered. The only thing we are going to discuss is this pink region of the model, which is the static mixing, in the sense that I have a reagent command that, okay, in cascade, basically it will be hopefully close to the actual flow of reagent measured by the flow sensor. I will have some water flow command. Water will be denoted with letter A in these pictures because the Spanish word agua starts with A, and I first recorded the Spanish. Sorry, but okay, A is water. Hopefully this water flow command will be close to the water flow reading, of course. And what are the equations of the static mixing? Well, total flow is sum of reagent plus water, and the static mixing instantly achieved concentration of the inflow to the tanks is reagent flow divided by total flow. So this is our model of the static mixing. So our discussion on control of the static mixing will assume that, okay, somebody will decide what to do in a master level control loop we are not considering. Somebody else will also devise a concentration controller in this master loop we are not going to consider. And then we'll have a level control action nu1 and a concentration control action nu2 that must be somehow translated to reagent and water set points. So we must decide what to do in this orange block with question marks. So we are going to model and linearize this pink segment and justify that when the water operating point is larger, that this multiloop strategy is the one advised. So we'll concentrate on this part of the video and we'll use MATLAB for that. So let us introduce first the model in the symbolic math toolbox by defining some symbols that we will manipulate. R will be reagent flow, W will be the water flow, so it's A in drawings, but I will use W here because changing text in MATLAB code is easier than changing text in drawings. So R and W will be inputs, and Q and X, total flow and reagent fraction, will be the outputs of the model, and this will be the equations of the model as we said in the drawing. There was A, now it's W, but it's the same. Once we have this model, we can linearize it. So the right-hand side of the model, we compute the partial derivatives with respect to reagent and water flows, and telling it to simplify whatever it gets, we will have a matrix of partial derivatives, but then we must replace the letters that appear there by the operating point. So we must replace R and W by the flow operating points. And then we will first start with a numerical example, considering that our reagent operating point is 1 liter per unit time and our water operating point is 5 liters per unit time. So the total output flow operating point is 6 and the reagent fraction is 1/6. So when I substitute these operating point values into the partial derivatives, I get this matrix that, if this were the linearization of a dynamic model, will be a transfer function matrix, but as this is a static model, it's just the gain. No dynamics, no Laplace transform or whatever. So good. Let us recall what are the inputs and outputs in here. Increment of total flow, increment of reagent fraction is this matrix times increment of reagent flow at input, increment of water flow at input. This is the linearized model. In order to justify that in this operating point we can propose this pairing, level control acting on the water and concentration control acting on the reagent pipe, well, how do we justify this choice? We will compute the relative gain array, which has this formula: gain multiplied element by element by the gains inverse transposed. So the result is this relative gain array, and the recommended pairing then is close to 1, this thing. So to achieve a given increment of total outflow, I will use increment of water, and to achieve a given increment of inflow concentration, I would use the increment of the reagent flow input. Of course, this flow will be associated to level control, mu1, and this concentration will be associated to overall outlet concentration control, mu2. This is how the static mixing in this operating point is recommended by the relative gain array. If we now substitute a generic operating point, uncommenting this and commenting below, then this J is just partial derivatives whatever, and the relative gain array has this nice form. It's built by just putting the nominal reagent and water flows divided by the total nominal flow, which is the sum. So if water is the larger flow in our operating point, then this would be the pairing that is recommended, which, okay, this was our case. We have a ratio of 1 reagent to 5 water. But in the case that the ratio was, let's say, the opposite, 5 reagent, 1 water, then relative gain array would recommend this other pairing. So basically, if we have more water than reagent, then we will control level with the water valve and concentration with the reagent valve, and vice versa. If we just want to slightly dilute the reagent and we have more reagent than water, then we would control level with the reagent valve and concentration with the water valve. So this is the conclusion of the relative gain array methodology for static mixing, and we'll end here. In summary, we have modeled this static mixing part of an overall larger control system involving level and concentration control of some tanks, but okay, the linearization of this pink part recommended us in a multi-loop setup to pair the desired flow increments for level control with the water, because we have more water, 5:1, in our particular operating point, and to pair the inlet concentration increments to the reagent valve. So, of course, apart from increments, the actual block diagram will need to add the water operating point to transform incremental actions to absolute set points for the flow valves, and again also the incremental actions from the concentration controller, adding the reagent operating point, will be transformed to absolute actions as a set point for the cascade controllers that in due course will try to follow those set points. So we'll end up here, and we will change this by some ratio control and decoupling options in forthcoming videos. For the moment being, this is all. Thanks for your attention.